Welcome to the presentation on logarithms, part 3. In this presentation, we will take a look at logarithms with bases other than 10. We'll introduce a natural logarithm, also known as simply ln, and solve application problems involving half-life. Let's get started. First, some refreshers from part 1. We had already looked at something of the form log 10 to the 7th and determined that that was equal to 7. And when we write that expression, we assume that there was a hidden base and the hidden base was 10. So if no base is written, automatically the understanding is that the hidden base would be 10. In other words, these two expressions are identical, whether I write log 10 to the 7 or log base 10 of 10 to the 7. Both of them represent the same thing. Because 10 is such a commonly used base, we just end up writing it as log. But what about other bases? So for example, log base 2 of 2 to the 7. For the same explanation that we provided in segment 1, this is going to be equal to 7. Basically, logarithm of a quantity gives you a certain power. If your base is 2, then log of a number only reports the power of 2, in this case 7. If the base had been 3, the log of a number would only report the power of 3. So depending on what the base is, as to what power will be used. So again, continuing on with log base 2, if I write log base 2 of 2 to the 3rd, the answer would be 3. Again, in base 2, logarithm only reports the power of the number 2 that was raised to a base of 2. So log base 2 of 2 to the 3rd equals to 3. Let's take a look at some other examples. First of all, if I write log of x equals 5, we had seen in previous videos that this indicates x is equal to 10 to the 5. Again, that's because the hidden base is 10. And to get an answer of 5, that means you need to have 10 to the 5 here. And that's exactly what we write as the answer, x equals 10 to the 5. But when you're dealing with different bases, the same idea holds true. It just will look a little bit different. So for instance, if we have log base 2 of x equals to 5, then what will x be? Remember, to have an answer of 5, you need to have 2 to the 5 here, right? If the base is 2, so x will be 2 to the 5. You may see a pattern emerging, and that is, if you have log base 2 of x equals 5, the way it works is 2 to this power equals to that quantity. And that's what we have here. And even more generally, instead of a base 2, if you have any base a, such as log base a of x equals to a power p, then we can write that x is equal to, so what is the value of x? Remember, you will try to write x as a to a power, and that power is your logarithm. So x equals a to the p. So once again, this number to that power equals that, and that's what we're seeing on this side. But notice the double arrows going both directions. So if you start with the right-hand side, that x is equal to a to the p, you can also rewrite that in logarithmic form, where you can say the power p equals a logarithm, and that logarithm is the base is a and the value is x. So you can go back and forth from logarithmic form to exponential, or from exponential form to logarithmic using this basic equation. This actually is also used as a definition of logarithms. And just something to notice here is that both a and x have to be greater than 0 to be well defined. Okay, some more examples. Say if we have log base 5 of x is equal to 3. What is x? So based on what we have just learned, x has to be 5 to the 3rd power. And if you like, check it, put that value back in here, and you're going to get 3. Now, if we go backwards on the next example, so suppose you are given that 7 is equal to 5 to the p. Let's recreate the answer together. So if 7 equals 5 to the p, find the value of p. If that is the question, then p equals, remember this power is a logarithm and it comes with the base 5. So this is going to be logarithm base 5 of 7. Some more properties of logs are indicated on this page. Some of these we've already seen. All I have done here is rewrite them with a different base, in general base a. We had already seen that log of base 10 of x times y equals log of x plus log of y. The same rule holds true when the base is any number a, any number greater than 0. So it doesn't have to be 10, it can be any base, and the same rule applies. We had also seen this rule. Similarly, log of a quotient is difference of the logs. Just make sure you have the same base used on both left-hand side and the right-hand side. And another rule that we had seen previously, it's not even a rule, it's pretty much our definition of logarithms, is that log base a of a to the r equals r. Remember, if the base here matches the base there, logarithm will only give you the exponent, which it does here, which is r. Now, what if these two are not the same? This a and that a are not the same. We can still simplify that, and I will call that rule number 4. Logarithm base a of b to the r is r times logarithm base a of b. So it's as if you took this power and moved it up front as a coefficient, and that's our property number 4. And what about the famous natural log function, as I have indicated, also represented by simply ln? That is the logarithm to the base e, where e is the famous Euler's number 2.718. It's a non-repeating decimal. So in general, if we write ln of x, or natural log of x, it's understood that this is logarithm to the base e of x, but we never bother writing down base e or log base e. Instead, the shorthand notation is natural log. Right now, it might not appear to you that this is indeed a natural log. The e may not look like a natural number, but those of you who may be taking calculus in the future will see that indeed many calculations in calculus are easiest when base e is used, and that's perhaps why, or one of the reasons why this base may be called as the natural logarithm. Now let's take a look at some properties using natural logs. So everything we've learned up to now still hold with natural logs. So instead of log of x times y, I can write natural log of x times y. And by property number 2, we saw in the previous page, you can write this as ln x plus ln y. Similarly, you can write something like that for ln x over y, which I did not write here, but that will be subtraction in the middle. And what about ln of x to the r? That was our property number 4 from the other page. That is, again, you can bring the power r down, r times ln x. And finally, what if you have something like this, ln of x equals to 5, and solve for x? In this situation, you may have to remind yourself that ln x is nothing but log base e. So if you have log base e of x equals to 5, what is x? Here you would have to use that property number 1 from the first slide, and the idea was e to the 5 will equal to x. So x equals e to the 5. So use e as any other base, and you can apply any of the rules we've seen so far. Okay, some more examples using the natural log. So for example, ln of e to the 5. The answer there will be 5 because, again, if you think about the fact that ln is log base e, so now you have log base e of e to the 5. And as of our first segment on logs, we had seen that if you can write this number as a power of that, whatever the power is, that becomes your answer. So in this case, log base e of e to the 5, the power there is 5, and our answer will be 5. ln e, by the same explanation, think of it as e to the 1, so the answer will be 1. So again, it's the base you need to raise, rather it's the power you need to raise e to get e to the 1, and that power you need to raise e is 1. The answer is 1. This comes up very often, so it's good to know that ln e is 1. And what about ln of 25? In that situation, we don't know 25 as e to an exact power. So in that situation, it would be perfectly fine to use a calculator. So you can simply go to your calculator and you will see that there is two bases are presented there, natural log or base e, and also log or base 10. So ln key is one of the keys in your scientific calculator. So you can just press that key and then 25, and you will see the answer will be roughly 3.219, let's say 3.219